Hello everybody! Today we're going to talk about magnets. I have actually just here a magnet. And here I have a rock, which is composed of metal. And if we take the magnet and put it on the rock, we see that it sticks together. Today we're going to do some experiments with magnets and talk about them. This magnet looks symmetric, but actually it's not. It has a north pole, which we represent by red, and a south pole, which we represent by green. If we take two magnets and try putting two south poles together, they will repel and won't want to stick together. Same if we take two north pole. They will also repel and not stick together. But if we take one north pole and one south pole, they will attract themselves and stick together. How does magnetism work? To find out, we interviewed Nicolas Dupuis, a well-known physicist at the CNRS and Pierre and Marie Curie Institute.
So this is not a very simple question. So in nature there are four fundamental forces or interactions, physicists would say. The first one is the gravitational force, which is, for instance, responsible for the attraction between planets. There are two other forces which are responsible for the stability of the nucleus of the atoms. And the last force, which is one of the most important ones for our daily life, is the electromagnetic force, which is actually both an electric and a magnetic force. So as you know, when you have electric charges, there is a force between these charges, the Coulomb force. Charges can be either positive or negative. If the two charges have the same sign, they repel. And if one of the charge is positive and the other one is negative, the two charges will attract. This is the electric force. Now when the charges move, there is another force which is called the magnetic force. And what we call magnetism is all the consequences of this magnetic force.
Why is the Earth a magnet?
So to understand why the Earth behaves as a magnet, I should first explain a very basic phenomenon of physics. When an electric charge moves, it creates a magnetic field. So when there is electrons moving in a solid, for instance, in a metal, that's the case when there is an electric current, then there will be a creation of a magnetic field. Now when we look at the Earth, it seems that the Earth is solid. Okay. Of course, there are seas and oceans, but below the seas, below the oceans, the Earth is solid. This is, however, not true if we look at the inside of the Earth. Deep enough, the temperature of the Earth is very high, the pressure is also very high, and in fact, the Earth is liquid. And in some part of the Earth, there are liquid metals, for instance, iron or nickel. And because they are liquid metals, there are electrons and ions moving inside the Earth. And this motion creates currents, which in turn create magnetic field. And this is the origin of the magnetic field created by the Earth.
Why are some metals magnetic and not others?
So to answer this question, I will consider the example of iron. So as you know, a solid is a collection of atoms. The atoms are fixed at given position in space. This is why we call it a solid. We cannot deform the material. Now if you look at irons, an iron atom behaves as a very, very tiny magnet. So when you put these atoms together to form the solid, you have a collection of many, many, many very tiny magnets. And in some conditions, it turns out that all the magnets, they point to the same directions and they create a big magnet. And this is this magnet that you can observe when you play with a magnet, for instance.
To make that, I used some iron fillings which get attracted by any magnet. I placed a magnet under the sheet so we did not see it. You can try this at home. It's pretty easy and gives a beautiful result. What can we do with magnets? Magnets can be used in lots of ways. The oldest way is the compass, which indicates the north. It also been used to store information on computer hard drives. Magnets were also used for trains. If we replace the rails and the wheels by magnets, we can make trains levitate. This means they will be 2 or 3 centimeters above the rails. If they do not touch the rails, this lets them go faster because we do not have the friction of touching the rails.